All right, well, thank you guys for coming. So yeah, today I'm going to talk about my work with these degree methods for polishing aluminum and for anodizing aluminum to produce nanoporous aluminum oxide templates. So to start, we need to talk about nanoscience with the nanoporous nature. So when we talk about nanoscience, nanoscience is the area where classical mechanics and quantum mechanics overlap. When you get to very, very small things, quantum mechanics is good at describing how things work. When you're dealing with very big things, classical mechanics describes how things work pretty well. But in the middle ground, there's an overlap where neither fully describes situations well at all. And so we use sort of a combination, both in its own field. Now generally, we are talking roughly in the 1 to 100 nanometer range, but that isn't a set range. And that's why with this sort of blue area here, that it kind of trails off on either way. It could be a little smaller than 1 nanometer, a little bigger than 100 nanometers. And these include things such as larger molecules, all the way up to viruses, sort of size. When we consider things in nanoscience that are different, properties don't act how we would expect them to on the classical scale. An example would be melting point, where melting points can be very different at the nanoscale, or Ohm's law, which doesn't apply in the exact same way on the nanoscale. So these physical properties don't apply in the same way. Now, when, we have this area, this range, and that's great. We can study that. But then we are also interested in how we apply the concepts we might know and the things we figure out at the nanoscale for applications. And this is the area of nanotechnology. Now, nanotechnology first started roughly, it's largely assumed to have started from Richard Feynman's 1959 talk. There's plenty of room at the bottom. Now, in 1959, most of the things that Richard Feynman proposed were completely science fiction at that point. Things like direct imaging of atomic structures, small machines on the nanoscale, or quantum computing, all of these ideas were well out of reach in 1959. If you fast forward to today, many of those things we've actually been able to accomplish, but there are still some things that we don't have accomplished that Richard Feynman had proposed. One of those things is very small machines. Very small machines in the nanoscale we do not have at this time. Applications for that might include things like nanosurgery, other things like that. So there are lots of unexplored areas in nanotechnology. Just one concept that you might have here is the concept of nanotweezers. Now this is similar to optical tweezers, which is what the 2018 Nobel Prize was awarded for, was for these optical tweezers and their applications. But nanotweezers would have a different approach and would be able to do some of those things that optical tweezers can do, but also more things. Examples being positioning of single emitters wherever you would like them in an atomic structure or any structure in general, which could be very useful rather than having to try and place them using some chemical method, which can be challenging or expensive or both. Also, trapping of these nanoscale biological specimens is something where you could actually take individual virus particles and have them trapped and then do work with them, even on individual cells that you could trap. Cells, not biological cells, but cells that you would do chemistry on. And then finally, the precise arrangement of atoms. We can already do precise arrangement of atoms using techniques such as STM, but using it in an easier way to exactly position atoms wherever you want them. And this is just one concept within nanotechnology that we could explore. And there are vast areas that you can go with all this. But these things still are relatively out of reach because we don't have the ability to make very small robotics, very small products on the nanoscale. So we need to be able to make components that would work at the nanoscale. One of these components would be nanowires. Now, nanowires have high aspect ratios and exist, as you would expect, at the nanoscale. These nanowires can be made of metals, as they generally are, as in this image where they're made of gold. But they could also be made of polymers or anything that can reasonably be made at this scale in repeating structure. So being able to make these is important. Making nanowires tends to be able to be accomplished through two methods. One of the methods is a self-ordering process, but accomplishing high aspect ratios to make longer and longer wires would be challenging and is not accomplished through just self-ordering methods, just through normal chemical syntheses. So we use templates instead to make longer and longer wires. So we need to have templates in general to make those sorts of things. Now, the most commonly used templates are aluminum oxide templates. This exploits a property of aluminum where put under electric potential, in the presence of certain electrolytes, the oxide layer will thicken and will have pores formed in the layer. These pores exhibit hexagonal cells in the aluminum oxide and expand vertically, essentially as far as you would like them to go. It was shown by O'Sullivan and Wood a long time ago that the thickness of the barrier layer between the aluminum and the actual air, as well as the pore diameter, are both dependent upon the voltage applied. So we can use these to make the aluminum oxide templates. Now, that was arguably still sort of theoretical up until the paper by Masuda and Fukuda in Science, where they were able to produce these idealized aluminum oxide templates. Now, these aluminum oxide templates were made under 0.3 molar oxalic acid at 40 volts for 160 hours at 0 Celsius. And those of us who have done work at 0 Celsius for 160 hours or any amount of time, we know that that is a long time to have something at that low of a temperature, and that is in and of itself a challenge. However, as we can see from these images, they form very, very ordered arrays of these nanopores in the aluminum oxide. They extend throughout, and they also extend vertically through the oxide layer. This was done in a 2-step process. So the last step being the 160-hour step. But that 2-step process was really different. And this paper by Masuda and Fukuda is the most well-known of actually producing these templates. So these templates are great, but they take a lot of effort to make. It is possible to buy these sorts of templates from Hopkins. Hopkins is arguably the only company that makes these templates. They are relatively expensive, but more importantly, they look like this. So this compared to the last slide, there are noticeable differences, such as the ordering and just the general look of these things. They aren't as open on the bottom. They are useful. They can be used very well, very easily, but they are reasonably expensive, delicate, and you have to use certain methods to mount them and use them in electrochemical experiments. They're good for filtering as well. You can filter at the nanoscale, but yes, so we can buy these, and that's great. Also, we don't have control over the depth, the sizing of them. You buy them as they are, and you use them. So we would like to be able to make something that has the quality of what Masuda and Fukuda produced, but in an easier time scale and using easier conditions for us to achieve. So we consider that, we pose that question, how do we do it? So one thing we want to consider when we have such a question of, oh, we're going to have a new way to make these, how are we going to do that? Is we want to consider the environmental impacts of anything we do, of how we're going to actually produce these things. So that leads us to green chemistry as a general concept. Now, green chemistry, just in general, is pretty straightforward in the sense that you want to make a more environmentally friendly system, product, everything. That includes obvious things like you might expect, like safer solvents, but also things that you might not consider as much, like energy efficiency and how you use energy in your chemical syntheses and in making your products and your products in general. Now, for research and especially in things like nanochemistry and nanomaterials, we don't necessarily know everything about the properties of the things we make, but we do our best and we do everything possible to make things as environmentally friendly as possible. Those things that you might expect are things like waste reduction, process safety, materials efficiency, and energy efficiency. All of which we need to consider in how we're designing our system and how we're going to make our aluminum oxide templates if we're going to make new ones. So, the method of making aluminum oxide templates is pretty well established. You start with aluminum metal, you anneal the aluminum metal to improve the grain structure. You mechanically polish with sandpaper. You then electropolish, and here's where we come to our first issue as far as green chemistry. So electropolishing of aluminum is generally and ideally done using perchloric acid at lower temperatures. Perchloric acid is an environmental concern, but it is also a safety concern. And you could see that partially from how we don't use perchloric acid here. We don't have a hood for it. We also just don't have the means to use perchloric acid. Perchloric acid can be explosive, depending on how it's used, and is generally not fun to deal with. So perchloric acid does really well electropolishing aluminum, but has obvious issues with it. I think it's interesting, in a lot of these papers, they say that they use perchloric acid at low temperatures, as the voltage through it, in order to prevent explosions. So they explicitly mention we use low temperatures to prevent the explosions. So an obvious safety thing that they want to consider. Then the anodization step. So anodization is generally done using things like oxalic acid or sulfuric acid, phosphoric acid. Those are the electrolytes that we're going to use to make these. In Masuda Fukuda's approach, they use oxalic acid, and that's a pretty common one to use. So that's generally the first step. Where we're doing a two-step anodization, then we have to dissolve the oxide layer. Now here's another issue as far as green chemistry, because this is generally done using chromic acid, which is not environmentally great. Chromic acid containing hexavalent chromium, which is an environmental hazard, a pretty serious one. So we're concerned about that when we're considering how we make these templates. And then you use a second anodization process, which would be largely identical to the first, and you're left with your aluminum oxide template. So we have sort of our scheme here. What are the things we need to change to make this better? Well, we want to change the electropolishing and the oxide layer dissolution steps. One thing that is pretty recent, that's a really interesting concept, are debutychic solvents. Many of them are green, and they're green solutions in both the chemistry sense of a solution, but also a solution like for a problem. So, how would a debutychic solvent works is that you combine two things together that have their various melting points, and then combine together in the correct ratios. The melting point of the mixture is significantly lower than the melting point of either substance you use. Now these debutychic solvents have properties similar to ionic liquids, but have some key differences as well. One of those differences is that ionic liquids tend to have, well, I'm sorry, they don't tend to have, they always have discrete ions. all the time. They have the cations and anions, and that's how the ionic liquid works. For the eutectic solvents, we have a hydrogen bond acceptor and a hydrogen bond donor. And the hydrogen bond donor doesn't have to be an ion, the hydrogen bond acceptor doesn't have to be an ion, but often is. In this case, this diagram here shows choline chloride and urea used in a 1:2 ratio. And how it works is that the hydrogen bond donors are essentially pulling away the chlorine atom from the choline chloride, and that is going to effectively lower the melting point. So these DSs that we can make tend to be made with things that you could consider green. Like choline chloride and urea are both reasonably good, not good for the environment, but aren't bad for the environment. Compared to ionic liquids, where many ionic liquids can have components that are not good for the environment. DSs do have some more reaction because they're not purely ionic, but they tend to be relatively unreactive as well, not as much as ionic liquids, but are still unreactive. So being able to use these DSs is going to be valuable if we're trying to make something green that isn't always considered green to begin with. So we have posed here the question, considered the ways that we're going to do it. That leads us to the hypothesis of this entire work, which is that the production of nanoporous aluminum oxide templates can be performed with purely green and relatively inexpensive materials at room temperature with inexpensive equipment and with relative expedition. Now, the inexpensive materials and inexpensive equipment are reasonably self-explanatory. We would like anybody to be able to do this. We don't want the buy-in to be massive to be able to make these. It would be ideal that any university on the planet would be able to make these. The relative expedition concerns that 160 hours you might see with Masuda Fukuda. We'd like to trim that down a lot. The room temperature has to do with the energy efficiency, but also has to do with general ease of use as well as safety, because things at room temperature tend to be safer than things at very high temperatures, for example. So accomplishing these requires a different setup. I say different because it's not as common to do electrochemistry in an open beaker setting. Oftentimes you use an electrochemical cell or some other apparatus for them. But in this case, we were able to use a beaker to accomplish everything we needed to. So we have a beaker on a stir plate with a water bath if any of the processes were significantly exothermic that might raise the temperature. These processes tend to be temperature dependent, so trying to keep that temperature as even as possible is ideal, especially at room temperature where it might change you don't want to get far from room temperature. The cathode we used in these experiments was a 304 stainless steel piece of metal, and that was it. A really reasonably inexpensive cathode. We used platinum, for example. The aluminum disc and the aluminum discs were punctured with aluminum wire, reasonably inexpensive, and the back was coated with GB liquid electric tape that you can buy at Lowe's, which is where we bought it. Again, inexpensive, easy to get material. The power supply used was a BK Precision 1698, which is reasonably inexpensive, as well as the Fluke 45 digital multimeter, which is also reasonably expensive, as well as being discontinued by Fluke, an older model. All of these materials worked for us and fit into that scheme that we had where anybody can do it. Anybody can use these things. The buy-in for this setup is very, very low. So with the Fluke 45 digital multimeter, we wanted to capture the data. If you're doing this knowing it will work for sure, you wouldn't necessarily need to capture all the data, but we needed to capture the data, as you might expect, to prove all these things, to show that they work. So we had to design a lab view program to capture the data and present it in a way that we can use. The lab view program that we had made is pretty simple. It consists of getting the current as well as the electric potential and the time, and gives a readout like this. Wow. Now that this front side is reasonably straightforward. The back end, I'm not going to spend too much time on because it's reasonably cluttered. But we have just a general flow where we have the information come in through the system, it's recorded with the 2 measurements, and then the files are opened and it's written to the files, pretty straightforward. And then this down here just for timing, just to make sure the timing is right. So this program works to produce those files, and that you can then use those files in Excel, produce the graphs, everything works out fine. So this is what we did for our electrochemistry experiment, which is everything that we have done. For electropolishing, to move into that, electropolishing of aluminum does have a published greener method called the bridal solution. Now, a bridal solution is made with 15% by mass sodium carbonate, 5% by mass sodium phosphate, and adjusted to a pH of 13, being a water solution. This solution is used at 80 Celsius and is done at roughly 5 volts and then a lower voltage, 2 volts, down to half a volt for the electropolishing of the aluminum. One of the issues, as those of you who have heard me say that I know might be thinking, is that if we're using an open beaker system and we have a water-based solvent for or a water-based system for our electropolishing, that at 80 Celsius, it might not work very well. It might evaporate pretty quickly. You probably aren't going to be able to use it for a very extended period of time. For these electropolishing methods, we have to electropolish for up to an hour at a time. That would be challenging, and that's exactly what we found. When we had done the bridal electropolishing, it works very well. On the left side here is just a sanded piece of aluminum that was already annealed, and as you can see, has defects at the micrometer level. When it's electropolished using the bridal solution, it has some defects still, but is very well polished. This result we could not reproduce because of this same issue with the beaker, open beaker system. So the bridal electropolishing method works well, but there are challenges, especially having it work without a special apparatus. In addition to that, the 80 Celsius with a basic solution, while still better than using perchloric acid, for example, isn't the most ideal situation for safety concerns as well as energy use and things of that nature. So we did recognize that this worked, but we wanted something even better than that. So we moved into the deprotecting solvents. Now, one DS that works, and that we have that there is published information about it working for electropolishing, is using a choline chloride ethylene glycol DS in a 1:2 ratio. So that works pretty well. It produces a situation like this, where at 7 volts, you're able to electropolish aluminum to make it reasonably defect-free. Now, this aluminum, 99.5% aluminum here, works well enough when it's polished with ethylene glycol DS. This is done at room temperature, so we're getting better. However, one of the issues is that ethylene glycol is not environmentally great. Still better than you would say maybe chromic acid or chloric acid, things of that nature, but still not good, which is why the ethylene glycol that we use in our antifreeze, we're trying to move away from to other sources and just use less in general. So we decided to try using a slightly different DS. In this case, we switched the ethylene glycol with propylene glycol. Propylene glycol, which you'll find in your food if you read the ingredients of your food, pretty common food additive, that combined with choline chloride. Choline chloride being a pretty common additive, as well as things like chicken feed, like that. So very common materials. Now, the choline chloride propylene glycol DS, published information indicates it works at a 1:2 ratio. However, those are under very specific conditions where you try and keep everything nice and contained. Under real conditions, especially in an open beaker, the 1-to-2 ratio does not work. 1-to-2 molar ratio. So we found that 2.5, excuse me, or 3 ratio works better. So that produces the DS just fine. You mix the two things together in those ratios, makes DS just fine, especially with a little heat, everything works fine. But then electropolishing becomes a little more challenging because the propylene glycol DS is less conductive than the ethylene glycol DS. And when we're trying to electropolish, we want to have something that's conductive. That required us to change the electric potential applied a little bit, but it still works at 10 volts or so. So at 10 volts, using just 99.5% aluminum, we get this polishing. Now this polishing, although there are still some defects, you could compare to the bridal electropolishing method or the ethylene glycol electropolishing. There are still defects and it still works. Now, because the conductivity is lower, in general you would need more time for the same polish as something that's higher. For the bridal electropolishing, you can get current densities up to about 100 milliamps per square centimeter. For the ethylene glycol DS, it's about 15 milliamps per square centimeter. But for the propylene glycol, it's 8 to 6 milliamps per square centimeter. So a lower current density means we're going to need longer time to make it work. With longer time, you would expect some of these defects to go away as well. Now, with higher purity aluminum, we see that there are even fewer defects for the same amount of time. And at a pretty zoomed in magnification, there are arguably no defects in this area. There's still some if you go looking for them, but the polishing works well. It provides us with a reasonably flat surface for using the aluminum. Now the current density is higher for the 99.5% ethylene, I'm sorry, the 99.5% aluminum that was used in the electropolish with the propylene glycol DS, going to about 8 milliamps per square centimeter. It's a little smoother of a curve, but it goes down to about 6 milliamps per square centimeter with the 99.99% aluminum. Just for information here, the impurities, or the non-aluminum part of the 99.5% aluminum, tends to be iron or silicon. So that is a consideration in why this might be. Now, as far as current efficiency, the actual mass loss and the theoretical mass loss taken by integrating, not quite this graph because it's the current density, but the current, and then using constants to convert to a mass of aluminum. The current efficiency is 1 with respect to the errors that you would associate with both the integration as well as the large error that you could see with the balance with small masses. So we have good current efficiency. The current doesn't go elsewhere. It's used in the actual electropolishing method. For a better way of describing how well the polishing actually worked, one thing that we had done was use a laser to try and figure out the reflectivity. And how we are describing that reflectivity is the greater the reflectivity, the less scattering that you would see of the light from the laser when it is shining on a piece of aluminum. So when we place the detector before the aluminum and the laser goes to the detector, as well as after the aluminum, or we get these two sources, we can see that from that ratio, the reflectivity of the sanded aluminum, just the sand aluminum, is about 36%, versus the reflectivity goes up to 78% of the electropolished aluminum at 99.5% purity. You would expect, with more time, as well as higher purity aluminum, that these numbers would improve even further. So, the electropolishing of the aluminum works. The interesting part about this is we then were able to use this electropolished aluminum to see how well it works for our further processes. So, what are those further processes? Well, the actual production of the aluminum oxide templates is where we had to go next. So these aluminum oxide templates, we were going to produce, rather than with 0.3 molar oxalic acid, we used 0.75 molar oxalic acid. The premise being that it would improve the times that it takes to anodize it. So instead of taking 160 hours, we're able to accomplish it with just an hour of anodization at 50 volts. And that was done for the dissolution. What was done, the dissolution of the oxide layer in between the two steps, instead of using chromic acid, we used 2 molar phosphoric acid, which requires a little bit more care because it could be damaging to the aluminum if you let it go indefinitely, that you don't see as much with the chromic acid, but is significantly better than chromic acid as far as environmental concerns, being simply phosphoric acid. So, with those conditions in mind, we're able to use our propylene glycol electropolished system to make aluminum oxide templates. And these are the results that you get from it. So, as we can see from these images, we have a pretty clear ordering of the pores that are roughly 60 nanometers in diameter, as you would expect using 50 volts, from the direct proportionality of the voltage used and the diameter. And the polishing we had seen with the propylene glycol does not appear to have affected these very much. As you can see here, these look pretty good. These look closer to what Masuda and Fukuda had produced compared to the Wattman nanodiscs, as far as the general ordering and the structure here. So this is with 99.99% pure aluminum, so the slightly better purity aluminum. And so yeah, these work pretty well. To compare that to how it might work with, say, the bridal electropolishing, we did the same method, but with a bridal electropolished piece of aluminum, and we get roughly the same results. That we have the same pore ordering, we have the same diameter, we get roughly the same results. So both methods work, but the propylene glycol DS electropolishing does work to make a smooth surface that we can then use for the production of these templates. One interesting thing that was relatively serendipitous is that there was a crack in the oxide layer of the aluminum oxide template that was made with the bridal electropolished piece of aluminum. And what we can see here is not only are there still these pores that exist, but they extend vertically through, as you had also seen from the Masuda and Fukuda images that show that vertical extension of the pore throughout the aluminum oxide template in the aluminum oxide layer. So this is great. We were able to reduce these templates that exhibit the same structure that we're looking for, that we want. The thing that we wanted to be able to do as well is make it that we can directly use these templates for deposition of metals or anything else that we can deposit in these systems. When you use, say, Wattman nanodiscs, you have to use some sort of method to make the nanodisc, because it's aluminum oxide and therefore an insulator, you have to make it conductive that it can allow current through for deposition into the pores. One of the things that we can do here is gently lower the potential use of in the ionization at the end in order to produce a thinner barrier layer, because the barrier layer thickness is directly proportional to the voltage used. So if we gently lower the voltage used, then we can get a thinner barrier layer. If that barrier layer is thin sufficiently, then although it is still an insulator, then it's thin enough that current can pass through and that the aluminum that exists under it can be used as the electrode in electrochemistry. So we did this, and we were able to deposit copper using a copper sulfate solution into the pores. We get wires that look like this when we partially dissolve the aluminum oxide template away from it. We can see that there is the same sort of ordering of the pores of these wires, as well as that the wires are exhibiting this 60 nanometer in diameter property, which indicates for that it's from these sorts of pores. and that we can use these pores to make these sorts of wires. In addition to that, you could use any sort of metal or anything deposited in the pores to make wires of this size. So this is a really useful tool that we don't have to do other methods to make the aluminum oxide template an electrode. It simply works as it is, and we can keep using it as it is. So the actual production of the oxide layer, as far as the graph, there's this spike that you would expect in ionization, and it goes down to 15 milliamps per square centimeter. It lasts for an hour until you stop it. And if you change this time, you get a thicker layer, depending on how you want it. So you can simply let it go longer or shorter if you want a thicker or thinner layer, respectively. The dissolution of the oxide layer exhibits this bump here in the open voltage of the aluminum layer as it slowly climbs, indicating that the aluminum oxide is dissolved. Eventually it sees this bump, and then it settles back down right away. And this is seen in other papers where they're dissolving these oxide layers, so it's a very common surface. There's not information as to why this bump in the voltage occurs on the graph, but it was exhibited, for example, in Stein's papers on the subject. And also we can see from these ionizations that when we're dropping the potential used, the current density also drops. So it's not going to make a much larger layer on the bottom after you're done with your 50-volt system. But then with the barrier layer thing, that we slowly can reduce the thinner barrier layer to more easily allow the deposition in pores. So these things work very well with 99.99% pure aluminum. When we use less pure aluminum, we get these pores. Now, the pores are still worse looking, for sure. The oxide layer looks much worse. However, there's still the 60 nanometer pores that you can see in the oxide layer. This lends itself to consideration of further work into using the cheaper aluminum, the 99.5% cheaper aluminum. There are concerns about whether that would eventually be possible to use in really, really nice pores, to get really nice pores. Many people consider 99.5% pure aluminum to actually be an alloy of aluminum. So at some point that might be challenged. There is work done using pure alloys of aluminum to see if they exhibit these same properties, and there are those challenges associated. So that's more further work that we can do with this. So, to conclude here, the electropolishing method, traditionally used for chloric acid at low temperatures, we're able to use a choline chloride, propylene glycol, DES, at room temperature to get a good polish. Using a two-step ionization process, generally 0.3 molar oxalic acid is used, as well as chromic acid for dissolution. We use instead 0.75 molar oxalic acid and 2 molar phosphoric acid for the dissolution. But lastly, with the barrier layer thinning method, the deposition of metals without sacrificial metal is possible. And we showed that with the copper nanowires, that we can deposit metals into the pores and produce these nanowires. So thank you all for coming. I want to acknowledge Dr. Farr, my advisor, as well as Dr. Cranwick and Dr. Lipple here. Sean Love, who did some work with us, as well as the department and the college. So thank you guys. Appreciate you coming.
So Phil used "we" a lot. There wasn't a lot of "we" in that. That was a lot of Phil. Questions?
Yes, Dr. Drew.
When you consider propylene glycol, have you considered, and might it make any difference if the middle methylene in propylene glycol were replaced by an oxygen? So you'd have oxygen, CH2OH, CH2OH on the other side. So just replacing the middle methylene in propylene glycol with the oxygen.
Yeah.
Might that make a difference in terms of behavior,
Yeah.
the PPG?
So DSs, I would say, are amazing. I want to say that because they're an awesome point of research. They're relatively new. Now, there are people who have done research where they kind of do almost essentially what you were describing, Dr. Earlier, where they kind of just throw things at it and see what makes a DES at all and how it works. In general, when things were changed even a little bit, you vastly change the connectivity of the system to the point where it no longer works. So I have not seen anything.
Well, I wasn't thinking of just, randomly trying a bunch of different things. In particular, inserting the oxygen in that position would change the polarization aspect of things in particular.
Yeah. I don't have any information on that.
I'm just wondering, speculating, might that make a?
Yeah, my concern with that would be viscosity, because we're also trying to have a very viscous solution here. So with that, I would see challenges in viscosity as well as the connectivity, for reasons that I wish I could tell you why that is, but just from what I've seen in the research. When things are changed even slightly, as I experienced with the propylene glycol, adding a methyl group, which tends to not do a ton in the chemistry, drastically changed the connectivity of the solution.
When you compare the ethylene glycol and propylene glycol, you're taking hydrocarbons, where if you insert the oxygen, you change the polarity.
Right. And I would speculate too that that would do something. I don't know what. I wouldn't be confident that that would produce a better system for electropolishing, especially because that doesn't really change the hydrogen bond donors. When you change the hydrogen bond donors, you do get really different properties. But, for example, adding a glycerol in makes it not work in the slightest, rather than the glycols. But those work for different things. Or, for example, using lactic acid can work for different things, as Jake has done in our lab. But those sorts of things might not bode well for the properties we're looking for, specifically viscosity and conductivity. But I don't have more information for you about those other things.
Thank you.
Yes, Dr. Glasgow.
This is more of a vocabulary question than anything. On the fourth slide, you were talking about high aspect ratios for nanowires. What is a high aspect ratio, and why do you want to do that for nanowires?
Yeah. So aspect ratio, right, is we're going to have somewhat pretty well defined as the length divided by the width, right? So the reason why we want longer wires that have the same width is because then they can extend further while still being the same width, which has different properties associated with it.
Such as?
Well, the conductivity doesn't change at a macro level, but we don't know what the conductivity would change or the resistance would change for the wire at that level. But the more important thing is simply the size, and able to adjust the size however much we want it to be, because that's really important with a wire. As anyone who has done wiring knows, that if you get stuck with a length of wire you can't extend it further, then you have problems. And so if we're making very small systems and we're stuck with a length of wire, say from the self-boring process, we wouldn't be able to continue further. But if we're able to adjust it however much we want to, then we can keep going and just keep depositing more if we need better, longer wires.
Thank you.
Yes, Dr. Grant.
When you were talking about how things change in the nanoscale, you talked about melting point.
Yes.
You define the melting point of a molecule at the nanoscale.
So a molecule, depending on the size of it, wouldn't largely be considered nanoscale, but let's say a large molecule, if you do that. But
Can you go back to your slide?
yeah, we're talking glucose level.
Yeah, that was on the nanoscale, wasn't it?
Yeah.
Okay. So what is the melting point for a molecule? That's my question.
So-
You said it.
it would not
There you
exist.
go. Okay, good.
Because you would need multiple.
Okay, so how does the melting point change then at the nanoscale versus the bulk? So let's say we have a small array of molecules.
So if you have more than one,
Yeah.
well, then we can now consider more generally the idea of a melting point. Then there are fewer interactions to hold it together. So generally the melting point is lower. For example, with gold, you would expect gold to melt at a pretty high temperature, 900 some odd Celsius. I can't remember that directly, but around there. But if you put gold nanoparticles in an oven even, you start to get issues because they melt even, at lower temperature, lower than 500 Celsius, for example.
All right, thanks.
Why do the commercial templates look so bad? So what process, they're obviously using some different process, or is it like 80% aluminum that they're starting?
I would suspect they're still using higher quality aluminum. I don't know how good it is. I doubt it's the highest purity possible. I doubt it's 5N5 aluminum. But the reason why it's so bad, I would surmise, is that they aren't checking it to the same degree. They're not going to obviously take every single one and look at it with an SEM or something like that. But also, yeah, they're probably trying to do it as fast as possible without real regards to exactly how good it is. Especially because when you go look on websites like Sigmology type sites to see how they're sold, they're generally sold as filters because for a long time that was their primary use, and it's still largely their primary use, I guess. And so for filters, they work decently well regardless of how good the pores look, just as long as the things you're trying to filter actually get into the pores. Yeah, but I don't have answer because I did try and find out how Wattman does it, but as you might expect, they're not keen to just tell everyone how they do it. I would suspect it's that way. I would suspect they're probably not putting as much time into electropolishing because electropolishing can take quite a bit of time for diminishing returns if you're selling it, and especially if you're the only one who sells them.
So did you get any of your samples to look similar to the Hopkins sample? So I guess that's kind of my question, is that are we seeing kind of cherry pick samples from the work you did versus the commercial operation, which sort of would include all of those?
That's a good question. Throughout my samples, if you're to take especially individual samples, you see the pore structure through it. There are some areas that are going to be worse than others, as you might expect. I did attempt to take sort of a middle ground. There may have been some areas that were slightly better, some areas that were slightly worse, but I wanted to take a middle ground of those. I did not experience in any of my imaging something that looked like Wattman's interfaces.
Okay.
That being said, it's possible. I I can't say I looked at every square in my finger. Yeah, it's possible. I don't, the interesting thing with Wattman's is that all of them look like that. When you keep looking at it, keep looking at them, they do all look like those.
So their early ones did. Their early ones were better, not nearly as good as the other ones, but their earlier ones were better than they are now.
So sorry,
No, that's okay.
is there a difference in scale? So how big are the templates that you get from Wattman versus how big of a macro scale are you trying to do all the chemistry on?
Yeah, so I used sizes of aluminum ranging from 1 1/4 inch in inches down to a 1/2 inch diameter. The ones from Wattman sold are generally 1/2 inch diameter, and most of my images come from
An
1/2
inch.
diameter.
They do 13 and 25.
They do.
So basically exactly what he's doing.
So, yeah, from that, I use similar sizes. Now, for their thicknesses,
Yeah.
they use different thicknesses. Now, back to sort of the initial question you asked, there is a chance that I would say is somewhat large that Lockman uses what's called a hard anodization process. And what they do with that is crank the potential all the way up, essentially. Put past the burning point even of the material. And then after that point, it goes through this what's called hard anodization, where it almost instantly goes through the aluminum and produces these pores. There has been a lot of research into that. No one has been able to make a hard anodization process that produces as good of pores as the soft anodization. If I were to have found that, I would suspect it would be a hard anodization process to do that, because it would likely be cheaper as far as time constraints, although energy would be a different story.
Thank you.
Yes, Dr.
So Quibena asked me a couple weeks ago, what are the applications of stuff we're learning in organic chemistry? Because I can tell he was bored. So you're talking about aluminum oxide. Today we learned about polymorphs. What polymorph are you forming?
I knew this. I believe it's alpha aluminum oxide. Now, naturally occurring aluminum oxide, so aluminum forms a passivation layer of aluminum oxide under, interestingly, like almost zero oxygen conditions. It does it in astoundingly low oxygen conditions and on the order of picoseconds, which I think is really interesting. That aluminum instantly forms this passivation layer. Now, that passivation layer has more question about what that polymorph is. It could have some of the gamma aluminum oxide in there. And then you start to see, especially when you anneal it, that annealing produces a slightly thicker aluminum oxide layer, but still on the order of less than 500 nanometers. It's about 4 nanometers thickness for just room temperature, but annealing at 500 Celsius or so produces a thicker layer, and then that that annealed aluminum oxide layer tends to, I believe, go to the alpha state.
So my next question is, does the polymorph matter in terms of your current density and this formation of the AAOs?
I don't know if it does. I don't know if you can actually make a different polymorph using these techniques. Everything I've seen was using that it produces the alpha polymorph.
So we also talked about alloys today, and you said 99.5% aluminum is essentially an alloy.
Some consider it an alloy, yeah.
Okay, so tell me why some consider that an alloy.
Well,
And what type of alloy? That's the other question I have for you.
I don't know what type of alloy.
Okay.
I can tell you the number if that helps, but I don't think that's where you're going.
What do you mean the number?
So the alloys, and I don't know all this because this is metallurgical stuff, but like how it said 304 stainless
Okay,
steel,
yeah,
right?
I got you.
Yeah.
That-
Yeah, just the number that the metallurgists have described for what the alloy is. I believe that 99.5 is also called 6061 aluminum. So then if you asked about what an alloy is,
Yeah, I mean, so why would you consider 99.5% aluminum an alloy? And would it be an interstitial alloy, a substitutional alloy, like since iron and silicon are your major impurities?
yeah, I would think it would be substitutional, but I don't have good information on that. But I would think so from the sizes.
So, Quibena, do you agree with that based on the size of aluminum, iron, and silicon? I'm going to throw Quibena.
You're good.
No, I'm just messing with you, Quibena. You're good. Okay.
Yeah.
So for aluminum and silicon, okay, I can see that as being substitutional. Do you think iron has a similar? Because you got to be within 15% of the radius.
Right. stretch
Okay.
for that.
Okay.
But I honestly don't know.
You did a good job answering the question anyway. All right. See what's coming your way, man?
Other questions?
Yes,
Yep.
sir.
I ask a question I always ask students. What's next?
So I don't exactly know right now. Getting a research position at some laboratory would be nice. Probably on the coasts, I would imagine, if I were to get some. Probably not in Colorado. If I were talking ultra long-term goals, I have other interests in purely theoretical physics, like Bohmian mechanics, frankly, as well as computer science and artificial intelligence. Those two things don't exactly overlap, but nor do they necessarily overlap too much with this work. But yes, that's what I would expect next.
Thank you.
All right, let's thank Phil once again before we move to a bit more of a private. Thank you for coming.
Now it's asking you real.
What's that?
I'm not part of the council.
You've given me a lot of good ideas.